Welcome to Tomorrow Unveiled. I'm your host, and I want you to start today by just pulling up a mental calendar for a second. Go to the week of February 4th through February 11th, 2026.
Right.
Usually when we look back at a specific week in tech or, in the energy sector, we see one big headline, maybe one company IPOs or a new bill gets signed, something like that.
Bingo event, yeah.
Exactly. But this particular week it was different. It didn't feel like a headline. It felt more like a shift in the underlying physics of our entire economy.
It's great to be here. And I could not agree more with that assessment. I mean, I've been tracking these industries for a long time, and progress is usually it's incremental. It's linear.
Yeah, a tiny step forward.
A tiny step. You get a solar panel that's, 0.5% more efficient. A battery gets a little bit lighter. But what our research team saw in this specific 7-day window was something else entirely. Okay. It was a convergence, a real one.
A convergence, that's the right word. It felt like we all collectively stopped trying to just, tweak the old system and finally committed to installing a brand new operating system altogether. We're calling our exploration of this for Tomorrow Unveiled Green Code Hot Core. And I think we should be really clear about what that means right from the start, because it does sound a bit like a sci-fi novel title.
It does, doesn't it?
Yeah.
But it's actually a very, very literal description of the engineering reality that we are now stepping into, the hot core part that refers to a full-on return to high-energy density physics.
Right. So we're talking about a change from the last decade or so.
A huge change. For the last, 15 years, the energy transition has been almost entirely defined by harvesting diffuse energy.
Wind and solar.
Wind and solar. And look, that is absolutely vital. We need it. But hot core is about binding atoms together in fusion, splitting them apart in advanced fission, and drilling deep into the Earth's crust to harvest geothermal heat.
So it's about getting the most power possible from the smallest physical footprint.
Maximum power, minimum space. That's the new game.
And then there's the other half of it, the green code. Because you can have all the power in the world, but if you're just pouring it into a leaky bucket, it doesn't really matter.
And that's the problem. Right now, our digital world, and I mean specifically the rise of artificial intelligence, is a very, very large and very leaky bucket.
This gets to the heart of what our research team has been calling the AI energy paradox, this central tension.
It's a huge paradox. We have this absolutely incredible tool in AI that we need desperately to solve climate change. We need it to optimize our grids, to discover new materials for batteries, to simulate reactor physics. I mean, the list goes on.
But the very act of running that AI
is consuming electricity at a rate that is, and I'm not being hyperbolic here, frankly terrifying. Data centers are becoming the new steel mills in terms of their energy footprint.
So the whole narrative of what we're digging into for Tomorrow Unveiled is really about how we solve that paradox. How do you feed the base while also saving the world?
And you solve it with this combination. You have the hot core providing the muscle, that dense, firm 204/7 power, and you have the green code acting as the nervous system, optimizing every single electron to make sure we aren't just burning power for the sake of it.
And what's so compelling, looking through all the source material our team compiled, is that these solutions they're not hypothetical anymore. We're not talking about maybe in 2050.
No, not at all. We are talking about concrete engineering breakthroughs that happened this week. I mean, we're going to talk about a fusion company using a manufacturing trick, a trick that involves bullet casings to save $100 million on a reactor.
That story is just unbelievable. We have to spend some real time on that because the physics are so elegant. And then there's China's artificial sun breaking a speed limit that scientists thought was a hard ceiling for plasma.
A hard ceiling, yeah.
Yeah.
And we have nuclear plants being designed that literally eat their own waste. They turn a 100,000-year storage problem into a fuel source.
And on the software side, just lines of code, software updates that are physically cooling down data centers without changing a single fan or a single piece of hardware.
It's an incredible slate of breakthroughs. It really does feel like a turning point.
It does. So let's not keep everyone waiting. Let's get into the machinery of the future.
Let's do it.
We absolutely have to start with the hot core, and specifically with fusion. Now, I feel like I need to preface this. For most of my life, fusion has been the running joke of the energy world.
Right. It's always 30 years away.
Always 30 years away, and it always will be. It's the science experiment that never quite graduates to being a power plant.
Yeah.
But looking at the reports from our research team about Pacific Fusion this week, The whole tone is different. The skepticism seems to be fading, replaced by something else.
It's being replaced by engineering pragmatism.
Yeah.
That is the fundamental shift. See, for 60, maybe 70 years, fusion was a physics discovery problem.
Yeah.
We were just trying to prove that we could, make it happen at all, get more energy out than we put in.
And we finally did that.
We did. Now we know we can do it. So the question has shifted from can it work to how cheaply can we make it work? And that brings us to Pacific Fusion and the incredible work they're doing with Sandia National Laboratories.
Our team really dug into the technical reports on this, and the headline is about something called a pulsar-driven method. Now, most people, when they picture fusion, they probably picture one of two things. Either the National Ignition Facility with those hundreds of giant lasers all focusing on one tiny pellet.
Or the tokamak, the big magnetic donut.
Exactly. But Pacific Fusion is doing something completely different.
That's right. They're using an approach called a Z-pinch. And to really understand why this week's news is such a massive breakthrough, we have to appreciate the sheer violence of a Z-pinch. You aren't gently heating the fuel. It's not what's happening.
So what are you doing?
You are taking a machine, in this case, it's based on the Z-machine architecture at Sandia, and you are pulsing about 22 million amps of electrical current through the target.
Hold on. 22 million amps. Let's just put that number in context. A standard lightning bolt is what, 30,000 amps?
30,000, maybe 50,000 on a big one. So you need to imagine capturing, roughly 700 to 1,000 lightning bolts, bundling them all together and forcing them to flow through a target the size of a pencil eraser, all in a fraction of a second.
In a fraction of a second? That's just an inconceivable amount of energy.
It is. And when you force that much current through a conductor, it creates a magnetic field that wraps around the current. And that magnetic field, it's called the Lorentz force, squeezes inward. It pinches.
The Z-pinch.
The Z-pinch. And it squeezes with such incredible force that the fuel inside is crushed and heated to fusion temperatures. It's brutal, it's fast, and it is brutally effective.
Okay, so the physics works. We know that. But the problem, and this is what really stood out in the reports, was the cost of the target itself. Why was it so expensive to shoot lightning at a tiny pellet?
It all comes down to a concept called premagnetization. See, you can't just crush the fuel. That's not enough.
Why not?
Because if you just crush it, all the heat you generate just leaks out before the atoms have a chance to fuse. It's like trying to compress a balloon that has a hole in it. The energy escapes. So before you crush it, you need to embed a magnetic field inside the fuel itself to act as a kind of thermal insulator, a trap for the heat.
A magnetic bottle, basically.
A magnetic bottle is a great way to put it. And historically, to get that initial magnetic field inside the fuel, they had to wrap the fuel target in these really complex, precision-engineered external coils.
Okay, I see where this is going.
Right. These coils would generate the magnetic field a few milliseconds right before the big 22 million amp pulse hit.
And I'm guessing that when you hit something with the equivalent of 1,000 lightning bolts and crush it into oblivion, the coils don't survive.
They are vaporized. Instantly. Gone.
Yeah.
So now think about the economics of a power plant. If you want to generate electricity, you can't just do this once. You need to fire this machine repeatedly, maybe 5-10 times a second.
And if every single one of those shots requires you to build and then destroy a pair of hand-wound, precision-engineered electromagnetic coils that cost thousands of dollars...
You don't have a power plant. You have a very, very expensive fireworks display. You're burning money faster than you're generating energy.
Right. It's a non-starter economically.
Precisely. And that has been one of the biggest bottlenecks for this whole post-fusion approach for years.
Yeah.
How do you get the cost per shot down from thousands of dollars to just pennies?
And this is where the bullet casing comes in. And I want to get the details exactly right here, because when I first read it, it sounded too simple to be true. The report says they replaced these complex coils with a piece of aluminum.
A simple, small cylinder of aluminum. It literally looks like a bullet casing or maybe the shell of a AA battery. But the genius here is not in the material. It's in the physics of how that simple cylinder interacts with that massive electrical pulse.
So what's the trick? How does a piece of metal replace a complex electromagnetic coil?
It's all about how magnetic fields diffuse or soak through metal over time. They realized that if they tweak the thickness of that aluminum casing just right, they could use the casing itself to do the job of the coils.
Okay, break that down for me.
So that massive 22 million amp pulse hits the outside of the casing. This instantly creates the magnetic field. Now, normally you'd want to keep that field on the outside until the very last nanosecond when you crush it.
Right.
But they designed this specific aluminum casing to be semi-permeable in a way. It allows a specific portion of the magnetic field to leak or diffuse through the metal and into the fuel before the casing itself implodes from the pressure.
So the casing acts like a time-release filter. It lets just enough of the magnetic field in to set the trap, and then wham, the rest of the force crushes the whole thing.
That is a fantastic way to visualize it.
Yeah.
The current running through the casing creates the field. The casing's specific thickness allows the field to soak into the fuel at just the right rate, and then the immense magnetic pressure crushes the entire assembly. The target magnetizes itself.
And just like that, you delete the external coils from the entire design.
You delete them entirely. And in the world of industrial engineering, deleting parts is the best possible way to save money.
It's the only way to scale something.
The report our team analyzed estimates this simple change eliminates about $100 million in reactor construction costs. We're just gone. Because you don't need all the complex machinery to place and manage those coils for every shot.
But the operational cost savings must be even bigger.
That's the real story. Operationally, it's a revolution. It turns the fuel target from a bespoke, handcrafted scientific instrument into a mass-manufactured commodity.
Like a bullet casing.
Exactly like a bullet casing. We as a species are very, very good at stamping out small metal cylinders by the billion. We have factories that do this all day long. Pacific Fusion is turning a complex physics constraint into a standard manufacturing task.
And that is why this feels different. It's not just another lab result. It's a blueprint for a factory.
That's it. It's the transition from science to industry.
And they have a timeline attached to this, right? I mean, they're not saying someday.
No, they're being very aggressive. They are publicly targeting net facility gain, which means the entire facility produces more energy than it consumes, all in by 2030.
2030. In the world of fusion, that is effectively tomorrow.
It's light speed. But they are not the only ones making these kinds of aggressive moves. We need to hop across the ocean to China. The Chinese Academy of Sciences released a really significant report on their East reactor.
Right. Now, this is a different beast. This is a tokamak, the magnetic donut we mentioned earlier, and the claim from them is that they've broken a kind of speed limit for fusion.
They have. It's called the Greenwald limit.
The Greenwald limit. Again, to the layperson, that sounds like something from a movie. What actually is it?
So in plasma physics, density is everything. It's the name of the game. The denser you can pack the plasma, that superheated soup of ions and electrons, the more collisions you get between the fuel atoms.
And more collisions means more fusion.
More fusion means more power. But for decades, going back to work by Martin Greenwald and his colleagues at MIT, we've known there was a theoretical ceiling, a limit.
A limit to the density.
A limit to the density. If you tried to push the density past a certain point, the plasma would become turbulent. It would get unstable and start to wiggle around inside the magnetic field.
Like a fire hose that's out of control.
That's a good analogy. And if it wiggles too much, it touches the wall of the reactor, cools down instantly, and the whole magnetic confinement just breaks. The reaction dies. It's called a disruption, and it can actually damage the machine.
So for safety, engineers have always designed their reactors to stay well below that limit.
Comfortably below it. It's the red line on the tachometer of your car. You know you can go past it for a second, but you really, really shouldn't. You designed the engine to run safely below it.
But the news from the East reactor this week, they didn't just nudge past the red line.
No, they didn't just nudge it, they buried the needle. The official report states they sustained operation at 1.65 times the Greenwald limit.
That's almost double what was thought to be the hard physical limit. How is that even possible without the machine tearing itself apart?
It comes down to some incredibly sophisticated plasma control. They figured out how to manage the plasma profile, the shape and the temperature gradient of the fuel inside that donut, with extreme precision.
What did they do differently?
They used a combination of advanced pellet injection to fuel the core and very careful magnetic shaping to create a super dense plasma in the middle while keeping the edge of the plasma relatively calm and stable. They essentially tricked the plasma into behaving itself at densities that, according to the old models, should have made it collapse.
So why does this matter for the rest of us? Why should you care if a reactor in China runs at a higher density?
Because, again, density equals power. The power output of a fusion reactor is proportional to the density squared.
So if you can run a reactor at, say, 1.6 times the density,
you can get significantly more power out of the exact same size machine. Or, maybe more importantly, you can build a much smaller and therefore much cheaper machine to get the same amount of power. It completely changes the economics.
it rewrites the business plan for fusion.
It absolutely does. Think about ITER, the massive international project being built in France. It's an incredible machine, but it was designed based on the old conservative limits.
Right.
If this new research holds up, and if we can replicate it in other machines, it means that ITER and all the future commercial reactors based on it, like China's own CFER, could be vastly more productive than we ever calculated.
It's like a free retroactive upgrade for every magnetic fusion project on the drawing board.
That's exactly what it is. It's a massive performance boost achieved through physics, not just hardware.
It's really fascinating how these two stories from two different continents and two totally different approaches mirror each other. Pacific Fusion is simplifying the hardware to make it cheaper. The East team is optimizing the physics to make the same hardware more powerful.
It really feels like the hot core concept is solidifying from theory into engineered reality. And you don't have to just take our word for it. The capital markets agree. We cannot ignore the flow of money here.
That's always the ultimate test.
And just this week, our research team tracked a company called Inertia Enterprises, raising a $450 million Series A round.
$450 million.
What?
For a Series A, that's massive. Usually a Series A is, what, 10 million? Maybe 20 if it's a hot sector.
It's unprecedented. And it was led by a top-tier firm, Bessemer Venture Partners. These are not unsophisticated investors. And they're not alone. You have another company, Avalanche Energy, raising $29 million for their very different compact fusion concept. The smart money, the people who do months of deep diligence, is deciding that fusion is no longer just a science project.
They're betting on it as a real asset class, an infrastructure play.
They're betting on the factory, not just the lab.
Okay, so fusion, for all its promise, is still the new kid on the block. But we have an incumbent hot core technology that's been around for 70 years. Fission, traditional nuclear power.
Right.
And frankly, for the last few decades, fission has been stuck. It's been seen as expensive, slow to build, and of course, plagued by the waste issue. But looking at the stack of research from this week, it really feels like fission is having a major renaissance.
It is. A huge one. And the key theme, the phrase you hear over and over again, is closing the fuel cycle. We were seeing a fundamental shift away from the old model.
The old model being?
Burn uranium once and then find a place to bury the waste for 100,000 years. The new model is circular. It's about recycling.
Let's talk about a company called Nucleo. They just raised $88 million, and their entire pitch is built around solving this waste issue.
That's right. And to understand what Nucleo is doing, we have to look at what nuclear waste actually is. When we pull a used fuel bundle out of a standard reactor, something like 95% of it is still perfectly usable uranium.
So it's not all just useless poison.
Not at all. Yeah. But it's contaminated with the other 5%. A mix of fission products and, most importantly, what we call minor actinides, elements like neptunium, americium, curium.
That's the really nasty stuff.
That's the really nasty stuff. These are the elements that stay intensely radioactive and radiotoxic for tens of thousands, even hundreds of thousands of years. They are the entire reason we need deep geological repositories like Yucca Mountain or the Onkalo facility in Finland. They are the long-term headache of the nuclear industry.
So Nucleo comes along and says, don't bury them. Burn them.
Exactly. They are developing and building lead-cooled fast reactors. Now, the word fast here is critical. Standard reactors, the ones we have today, use slow or thermal neutrons to cause fission.
What?
Fast reactors use high-energy fast neutrons. And it turns out that these fast neutrons are capable of splitting those nasty minor actinides. They can break them down into smaller, less harmful atoms.
So you take the longest-lived, most dangerous waste, you process it into new fuel, and you put it into this fast reactor. What comes out the other end?
Well, energy, first and foremost, a lot of it. They are generating carbon-free electricity from the waste. But the byproduct, the new waste that comes out, is mostly fission products that are only dangerously radioactive for maybe 300 years.
Wait, from hundreds of thousands of years down to 300 years.
That's the promise. And that is a fundamental paradigm-shifting change. 300 years is a manageable engineering problem. We can build a container, a building that we are confident will last 300 years. We cannot, with any real certainty, engineer something to last 300,000 years.
It basically solves the intergenerational ethics problem of nuclear power in one stroke.
That's the goal. And Nucleo is designing these reactors to run on what's called MOX, fuel mixed oxide fuel, which is manufactured directly from that recycled waste. They are turning a multi-trillion-dollar liability, the world's stockpiles of nuclear waste, into a strategic energy asset.
It seems almost too good to be true. If this technology works, why haven't we been doing it for the last 40 years? Why did we ever start burying the fuel in the first place?
It's a fair question. And the answer is really a mix of complexity and cost. Fast reactors are just harder to build and operate than standard water-cooled reactors. Liquid lead is a more difficult coolant to manage than water, and frankly, for most of history, digging fresh uranium out of the ground was dirt cheap.
So there was no economic incentive to go through the trouble of recycling.
None whatsoever.
Yeah.
But now, with the demand for clean, firm energy skyrocketing, uranium prices are climbing, and suddenly the math has changed. And the geopolitical security aspect has changed too.
Oh, so?
Nations are starting to realize that sitting on a giant pile of waste that is actually a massive reserve of fuel is a huge strategic advantage. And we see this in the U.S. as well. The Department of Energy's H Canyon facility at Savannah River.
That's a huge chemical separation plant, right?
Massive. And it's restarting operations specifically to recover usable uranium from used naval and research reactor fuel to create something called HALEU.
HALEU, right. That's high-assay, low-enriched uranium.
It's essentially the high-octane gasoline for the next generation of advanced reactors and small modular reactors. The U.S. government has woken up to the fact that if they want an advanced nuclear industry, they can't be reliant on Russia, which is currently the main supplier of HALEU. They have to, in effect, mine their own waste.
It's a complete reframing of what the resource even is. But, technology is only ever half the battle with nuclear. The other half, and usually the bigger, slower half, is regulation.
Oh, yeah.
The Nuclear Regulatory Commission, the NRC, they have a reputation for being, let's say, thorough?
That is the most polite way of putting it. Glacial is the word the industry often uses. But this week we saw a signal that the glacier might actually be melting. Just a bit. The NRC announced what they're calling a refactoring of their environmental review process.
Refactoring. That's a software term. You're using software terms for government agencies now.
Well, it fits. What they did was issue new categorical exclusions.
And what does that mean in plain English?
It means that for certain specific types of advanced reactors, we're talking small ones, on previously disturbed industrial sites, for example, they no longer need to write a 10,000-page environmental impact statement from scratch, a process which can take years.
So if the reactor design fits inside this pre-approved safe box,
It gets a pass on that specific, very large, very slow chunk of bureaucracy.
that must save what? Months? Years?
Years, easily 2 to 3 years off the project timeline, and millions upon millions of dollars in legal and consulting fees. It's a clear signal from the regulator that they are finally trying to move at the speed of the technology.
And the market is hearing that signal loud and clear.
Immediately. We saw Amazon putting serious capital behind modular nuclear builds, specifically to power their AI data centers. We saw Duke Energy, one of the biggest utilities in the country, filing for early site permits for SMRs.
And the one that really stood out to me was a company called Genex. They're a solar developer, traditionally.
That's right. Historically, all they did was build huge solar farms. But they just announced that they are pivoting their business to help site small modular reactors on the same land.
Wow.
This is the peace treaty in the energy wars that we've been waiting for. A solar developer finally realizing that their greatest asset isn't the panels themselves, but the land and, more importantly, the grid connection.
The point of interconnect.
Exactly. And if they can plug a small nuclear reactor into that same grid connection to sell power 247, especially at night when the solar panels aren't working,
Then they have a much more valuable, much more profitable business.
we have a 247 clean energy business. The whole renewables versus nuclear war is ending. It's becoming renewables plus nuclear.
This brings us perfectly to the third pillar of the hot core. We've talked fusion, we've talked fission. Now we need to look down.
Geothermal.
The heat right beneath our feet.
Now, when I think geothermal, my mind immediately goes to Iceland or Yellowstone. You basically need a volcano in your backyard. That's the old paradigm for sure. That's what we call hydrothermal resources. You needed 3 things to align: hot rock, permeable rock so water can flow through it, and a source of that water all near the surface. It's incredibly rare.
Right.
But a company called Fervo Energy is fundamentally changing that calculation. They announced this week that they successfully drilled their hottest, most productive well yet. And the key to the story is the location. They are not drilling into a volcano. They are drilling into sedimentary rock.
Sedimentary rock. So that's just layers of old dirt and sand that got compressed into rock over millions of years, right?
Exactly. Sandstone, shale, limestone. It's the same stuff the oil and gas industry has been drilling through for over 100 years. And that is the absolute core of the breakthrough.
What's the connection?
Fervo isn't inventing brand new physics. They are applying decades of oil and gas technology, specifically horizontal drilling and hydraulic fracturing, or fracking, to the problem of geothermal.
So they drill down a couple of miles, they turn the drill bit sideways, and then they fracture the rock to create a giant underground radiator.
That's a perfect analogy. They create artificial permeability where none existed before. They pump water down one well. It flows through that massive network of fractures, picking up heat from the rock, and comes back up another well as steam to turn a turbine.
And by proving they can get high-quality, high-temperature heat out of sedimentary rock, they've basically blown the world map for geothermal wide open.
Completely. Because while volcanoes and hydrothermal vents are incredibly rare, sedimentary basins are everywhere.
So this could mean you could have a geothermal power plant in West Texas or in the middle of Pennsylvania.
In vast swaths of the globe that were previously considered geothermally useless or cold, it expands the total addressable market for geothermal by orders of magnitude. Their new Project Cape Station is targeting 400 megawatts of firm dispatchable power as early as 2026.
400 megawatts is a serious power plant. That's a coal plant replacement.
It is. And it's firm. It runs when the sun is down. It runs when the wind stops blowing. It is the definition of baseload power.
But even with all this new firm power, you still need storage. The grid needs buffers. It needs shock absorbers. And our research team flagged some really interesting news this week about batteries that move us beyond the lithium bottleneck.
Yes, two huge stories here. First, we saw CATL in Chang'an officially launched the first mass-produced cars powered by sodium-ion batteries.
Sodium, so literally salt.
Yes, the fundamental chemistry is very similar to a lithium-ion battery, but instead of using lithium ions to carry the electrical charge back and forth, it uses sodium ions. And sodium, as you said, is just salt. It's abundant, it's cheap, and it's geopolitically stable.
So what's the catch? Does it work as well as lithium?
The main trade-off is energy density. It's not as energy dense. You won't be seeing a sodium battery in a high-end, long-range sports car or an electric airplane anytime soon. It's just heavier for the same amount of power. But it works much, much better in cold weather than lithium does. And it is significantly cheaper to produce for a small city car, for a home energy storage backup system, for grid-scale storage. It's perfect.
And it completely breaks the geopolitical choke point on the lithium and cobalt supply chains. We don't have to worry about running out of salt.
No, anytime soon. And then on the other end of the storage spectrum, for really long-duration grid storage, we have a company called Or Energy piloting iron-air batteries in France.
Iron-air batteries, I've heard these called rust batteries.
That's what they are. It's because the chemical reaction is literally rusting. To discharge the battery, you expose pellets of iron to the air, and as they rust or oxidize, they release energy.
Okay, so how do you charge it?
You run electricity back through it, which reverses the chemical reaction. It turns the iron oxide, the rust, back into pure iron. It's called derusting.
That sounds incredibly low-tech.
It is, and that is the absolute beauty of it. The ingredients are iron, water, and air. It's big, it's heavy, you'd never put it in a car, but it's dirt cheap. And the key metric here is duration. A good lithium grid battery is great for 4 hours of storage. An iron-air battery is designed for 100 hours.
100 hours, that's over 4 days. That's not just for shifting solar from day to night. That covers a major storm, a heat wave.
That covers a Dunkelfloat, a term from Germany for those dark, calm, windless weeks in winter where renewables can go to almost zero. That is the missing link for a fully renewable grid. Long-duration storage.
It's just amazing to see this evolution of the hardware. We're moving from these scarce exotic materials, cobalt, lithium, rare earth magnets, to things that are just abundant. Aluminum for fusion targets, salt for batteries, rust for grid storage, recycled waste for fission fuel.
It's a sign of a maturing industry. We are learning to do more with less, or at least with what we have in abundance.
We are going to take a quick breath here. We've covered the hot core in a lot of detail. Fusion, fission, geothermal, storage. But when we continue, we have to address the other side of this new operating system. We have to talk about the green code that manages all this new power, because without it, we're just revving a much bigger engine in neutral.
And honestly, the breakthroughs our team found on the software side this week are, in their own way, just as impressive as the physics ones. Stay with us.
Before we jump into that digital nervous system, just a quick note to our community. If you're finding this look into the hot core insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And for our listeners, on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and grow this project.
We also want to hear from you. We talked about SMRs, those mini nuclear reactors. So the question for the comments is this: would you live next to one? If it meant your energy bill was cut in half and your power was rock-solid reliable, would you be comfortable with a sealed underground microreactor in your neighborhood? Let us know what you think.
Welcome back to Tomorrow Unveiled. We've just spent a lot of time establishing that the hardware of energy is getting hotter, denser, and frankly, more powerful.
Yep.
But as we said at the top, we have a paradox. The explosive rise of AI is consuming energy at a rate that threatens to outpace even these incredible new sources.
The demand growth is just explosive. We're looking at projections from our research team where data centers could consume 10%, maybe even 20% of a developed country's total electricity supply within a decade.
That is just not sustainable.
It's not unless we fundamentally change how the software itself runs.
And this brings us to the Green Code. We saw a research paper this week that I really think is going to become a foundational text for software engineers in the coming years. It's titled Flip-Flop. Flip-Flop, a static analysis-based energy optimization framework for GPU kernels.
A real catchy title, but the implications are absolutely massive. Let's try to break this down. We all know GPUs, graphics processing units, are the workhorses of the AI revolution. They do all the heavy lifting for training and inference.
They're the engines.
But this paper claims they are lazy, or maybe just really inefficient.
Inefficient is the perfect word.
Yeah.
Think of a GPU as a gigantic factory floor with thousands and thousands of tiny specialized workers. These are the cores. These workers are incredibly fast at doing their specific job, which is math.
Okay.
But the problem is often the management. The instructions they're being given, the software code, can be very poorly organized. It often forces them to just stand around waiting for materials to be delivered from the warehouse, which is the memory. Or it makes them do work that isn't actually necessary for the final product.
So the chip is burning power, the lights are on in the factory, but the workers are just idle, not producing anything useful.
Exactly. It's executing useless instructions or managing memory in a really clumsy way. The flip-flop framework uses something called static analysis to fix this problem.
Explain static analysis to me. Is that like a spell checker for code?
It's much more sophisticated than that. Think of it more like a logistics expert for a fleet of delivery trucks. Without static analysis, the driver, the GPU, just gets a list of addresses and drives around, figuring it out as they go. They waste gas, they backtrack, they waste time.
Right.
Static analysis is the expert looking at the map and the full list of deliveries before any of the trucks ever leave the depot. It calculates the absolute perfect route. It eliminates all the unnecessary left turns. It groups deliveries by neighborhood.
So the software analyzes the structure of the code before it actually gets run on the hardware.
Correct. It looks at the kernel, which is the core calculation loop that gets run millions of times.
Yeah.
And it finds all the energy leaks. It might say, hey, in this loop, you're fetching the same piece of data from memory 5 separate times. Why not fetch it once, hold on to it, and use it 5 times?
Which would be much faster and use less energy.
Way less energy. Or it might find you're calculating this value, but then you never actually use the result for anything. So let's just delete that entire step.
And by cleaning up the instructions, by creating a better route for the data, you physically change the behavior of the silicon chip.
You directly lower the energy consumption. And because energy consumed ultimately becomes heat, you physically lower the temperature of the data center. This is the part of the report that blew me away. They achieved significant double-digit reductions in energy use for common AI tasks without changing a single piece of hardware.
That really is the green code promise. You don't necessarily need to build a new power plant if you can just make the software stop wasting the power you already have.
It reframes the role of a software engineer. Suddenly, every line of code they optimize is a gram of carbon not emitted into the atmosphere. They become climate engineers.
But the relationship between AI and energy isn't just a one-way street of AI using less power. It's also about AI helping us make more power more efficiently. We saw a collaboration announced this week between Westinghouse and Google that really illustrates this perfectly.
Yes, this is the virtuous cycle. This is the loop closing. Westinghouse is a legacy nuclear giant. They have operational data going back a century. They know how atoms behave in the real world.
But that data is often stuck in old formats, paper logs, old databases.
Exactly. Google's helping them take all that historical data and use it to train AI models that create digital twins of their nuclear reactors.
The digital twin, we hear this term a lot now. Is it just a fancy 3D model, like a level in a video game?
It's so much more than that. A video game model looks like the object. A digital twin behaves like the object. It simulates the actual physics, the neutron flux, the thermodynamics of the coolant, the fluid flow, the material stress on the pipes.
So you have a virtual nuclear reactor running inside a Google Cloud server that perfectly mimics the real reactor running in, say, Georgia or Pennsylvania.
And the accuracy is the real headline here. The report our team looked at stated the digital twin achieved 99% accuracy in simulating the reactor's real-world behavior.
99%. For something that complex, that's effectively perfect for simulation purposes.
It is, and it allows you to safely play what-if scenarios. What if we increase the power output by 2%? What if we try to extend the fuel cycle by an extra month to get more energy out of it? What happens if a critical pump fails?
You can crash the digital reactor 1,000 times in 1,000 different ways to find the absolute safest operational limits.
And then you can apply that optimized strategy to the real reactor to make it more efficient and safer.
So the AI helps the nuclear plant run better, which produces more clean power, which then powers the AI.
It is a perfect virtuous cycle. And it extends to things like licensing, too. If you can show the regulator the simulation data from a 99% accurate digital twin, you can prove the safety of a new design much faster than building expensive physical test rigs. It could accelerate the entire industry.
This broader concept of green ops seems to be taking hold everywhere now. Our team was looking at reports from the Armenia science body that talked about these trends in the wider coding community.
Green ops is absolutely becoming the new DevOps. It's not just about making code run fast anymore. It's about making it run efficiently. Companies are starting to audit their code for carbon intensity.
And they're also doing what's called carbon-aware computing.
Yes, shifting the load.
So the idea is, if the sun is shining bright in California, electricity there is cheap and green, so you automatically move your big AI training job to a data center in California.
Right. And then when the sun sets there, maybe the wind starts blowing hard in Texas. So the workload automatically migrates to a data center in Texas.
You're literally chasing the weather around the country.
You're chasing the zero-carbon electron. The internet itself is becoming weather responsive. It's a fascinating evolution of our digital infrastructure.
So we've covered the physics of the hot core, and we've covered the intelligence of the green code. Let's zoom out now to the global map, because none of this happens in a vacuum. It requires massive investment, clear policy, and of course, geopolitics.
And the global signal our research team picked up this week was unanimous, really. We are entering the era of firm power.
The International Energy Agency, the IEA, released a report that was pretty blunt about this, wasn't it?
They were very blunt. They essentially said that the era of just build more variable wind and solar is over. That was phase 1. We have now entered phase 2, where the grid is becoming saturated with that variable power, but overall demand is skyrocketing because of AI and electric vehicles.
So you have a supply that flickers and a demand that's always on.
And the only way to bridge that gap is with firm, dispatchable power nuclear, geothermal fusion when it arrives, and of course, long-duration storage.
And the money is proving them right. You just have to look at Japan.
Japan is the absolute canary in the coal mine for energy strategy. They have almost no domestic fossil fuels. They shut down their entire nuclear fleet after the Fukushima disaster. They've been incredibly vulnerable.
But that's changing.
It is. This week, their government approved a $780 billion budget for what they're calling the green transformation. That is an astronomical number.
And where is that money going?
A huge portion is dedicated to explicitly restarting their nuclear capabilities and investing heavily in next-generation fission and even fusion. They have realized that energy security is national security. They cannot be dependent on imported natural gas forever.
And then you have the Middle East. The traditional energy superpowers, they aren't just sitting this one out, watching their main export become obsolete.
Not at all. We saw multiple reports of preparations for $100 billion in annual investment in new energy. They are executing a pivot from being oil superpowers to being energy superpowers.
So not just renewables.
They are building massive solar arrays, yes. But they're also investing heavily in the cloud infrastructure to run AI and in things like green hydrogen production. They want to own the global energy market of 2050, just like they own the market of 1950.
And what about the UK?
The UK just completed what's called Allocation Round 7 for their contracts for difference. They are doubling down on offshore wind, which is their natural strength, but they are also carving out specific, separate funding pathways to encourage new nuclear baseload. They're trying to build a balanced, resilient portfolio.
We should probably touch briefly on the U.S. We have, let's say, a complex political landscape. Does the election cycle or which party is in power change this overall trajectory?
Our team analyzed H.R. 6938 and the recent appropriations bills looking for that exact answer.
Yeah.
And the result is, surprisingly, no. Not really.
How can that be?
The branding changes, absolutely. One side might call it the Green New Deal, and the other might call it American energy dominance. But when you look at the actual line items in the budget, the funding for H Canyon to recycle nuclear fuel, the funding for fusion research programs, the tax credits for new nuclear plants, it is remarkably bipartisan.
Because at the end of the day, everyone wants the same thing.
Everyone wants cheap, reliable, domestically produced power, and everyone in Washington wants to beat China in the next great technology race. That is a very powerful motivator that tends to transcend party lines. The hot core is politically durable.
So let's bring it all home. We've had a really dense hour. We've gone from 22 million amps in a Z machine all the way to the static analysis of GPU kernels. If you had to summarize this whole green code hot core thesis for someone who just tuned in, how would you distill it?
I would say this. We are witnessing a great convergence. The hardware of our energy system is getting smaller, hotter, and denser. At the exact same time, the software that runs our world is getting smarter, cooler, and more efficient. And the combination of those two powerful trends is what will move us from an era of scarcity to an era of engineering.
From scarcity to engineering, I like that. It reframes the problem. It stops being a question of, are we going to run out, and starts being a question of, how fast can we build?
That's it, exactly. The science is largely done. The physics works. Now it's a matter of supply chains and permitting reform and code optimization. It's an execution problem.
You know, we always try to end our sessions for Tomorrow Unveiled with a provocative thought, a what if to leave people with. And as I've been listening to you describe this convergence, AI optimizing fusion, fusion powering AI, waste becoming fuel, I'm struck by a really optimistic thought.
What's that?
We spend so much of our time worrying, and for good reason. We worry that AI will consume all our energy. We worry about climate change. We worry about resource wars. But what if this convergence actually works? What if the efficiency of green code and the sheer power of the hot core lead us to the exact opposite of scarcity?
You mean energy abundance?
True, genuine abundance. If electricity becomes virtually free and clean and available everywhere, the physical constraints on human progress just fall away. You can desalinate all the ocean water you need for agriculture. You can power machines to scrub CO2 directly out of the atmosphere. You can build massive vertical farms in the middle of every city.
It changes the fundamental economic equation of civilization. If energy is cheap, water is cheap. If water is cheap, food is cheap. If all those are cheap, then health and education can be too.
So the question we should leave our listeners with today isn't how will we survive the coming energy transition? The real question is, what will you build when energy is finally free?
That is a world worth working very hard to build.
It certainly is. Thank you for guiding us through the physics and the code today. It's been fascinating.
It was an absolute pleasure.
And thank you for joining us on this exploration of the future. This has been Tomorrow Unveiled. We'll see you in the future.